balance really ties back to something we've talked about before, so homeostasis. This idea that the body has to be in a constant state of balance all across with regards to things like temperature, pH, blood volume, etc., etc. And so balance here not only has to do with the kidneys and their function, their role in that job, but the bigger picture here. So the lungs also play a role in balancing the pH. And we'll talk about their role as we go on. So the first thing we'll talk about is that concept of balance. The kidneys have to balance the amount of pH, the amount of hydrogen ions, which is balancing the pH, by excreting, which is getting rid of some of that hydrogen, or reabsorbing some of that bicarbonate. So we talked about bicarbonate being absorbed in the proximal convoluted tubule versus hydrogen ions being secreted in the distal convoluted tubule. If you remember those two locations and those two processes, that has to be balanced. That's what the kidneys are doing. They're detecting the pH of the blood, and they're making a decision: should I absorb bicarb to make the blood more alkaline, or should I secrete acid on the other end? Alrighty. We also want to balance the movement of water, and we'll talk about how that happens in the loop of Henle. So we need to balance our input versus our output. So where are some areas that we input water generally? The GI tract. We drink water, we eat foods that have large water content, fruits, etc. So a lot of the water comes in the GI. Where else? Okay, what about outputs? Where do we output water? Urine is a big one, yep, correct. What else? Sweating, that's another one. Excretion or excrement from the GI tract as well. So there's inputs of water and solutes and other things, and there are outputs, and the kidneys must function to balance that. Okay? So they regulate the solute concentration, the amount of sodium, chloride, etc. Bicarb, they regulate the amount of water absorption. Should be absorbed more or less water. Now, where is this regulated water reabsorption? Just to remind ourselves. Where is this regulated water reabsorption? Is it in the PCT? Is it in the PCT? You just talked, it's not, right? Where is it? Where's the DCT and the collecting duct, right? So let's remind ourselves, the regulation of water reabsorption is in the regulation of absorption is in the DCT and the collecting duct. This is where things are regulated based upon hormones, which we'll talk about, such as ADH. And so these are based upon external factors. Now, we also have different compartments of the body that are transferring water or exchanging different amounts of water. We got cells, connective tissue, sweating, respiration. Cells being the area of the body that has the most water content. And so water can move in and out of the tissues, in and out of the cells. And so that has to be in the equation of this balance. Moving on here to objective 2, which is talking about different sources of that body water. Okay, and so in this schematic diagram, what we see is on the left, factors that affect input, such as the GI, the ingestion of substances, versus output, such as excretion, feces. There is a small water content in feces, right? On the right side of this schematic, we have the kidneys' role in all of this. So on the right side, we can see that on the other end, the kidneys are also helping to balance those points of output, so excretion of urine. All right, so let's talk about different states in terms of water balance. If we're nice and balanced and things are moving optimally, if we're at homeostasis, we're going to be in this first image. So in this first cylinder or this first jar in the image, right? So this one here on the left. This is what homeostasis looks like. This is what balance looks like. Inputs match outputs, and there's no change in the fluid volume. Okay, when we say no change, so this would be your blood volume. Think about this to be equated to things like your blood pressure, your hydration, your blood volume. The second image shows positive balance. And this is where water enters the plasma and then exits. So what happens here? What happens at this point? So this positive balance scenario. Right, so water's coming in faster and it's leaving. So you have an excess of water building up. What are some states that might remind you of? In terms of simple states. Edema, think about swelling in the body. You want edema, that's holding on to water. And that's your positive balance. What about your negative balance? This is where solutes are exiting faster than they are coming in. And so what's happening here? We have the opposite scenario. We have a drastic decrease in the the total fluid. And again, we're comparing this total fluid to things like your total blood volume, which will decrease or suffer if you have that negative water balance, that negative balance. What are some states that will remind you of this negative balance scenario? Sweating, dehydration, hemorrhaging, diarrheal states where you're severely, you have severe diarrhea, etc., etc. Okay? So these are things we want to bear in mind as we continue to talk about balance. Speaking about the cells that bring about balance, there are two cells we're interested in, the principal cells and the intercalated cells. Now these are cells in the distal tubules and the collecting ducts, and they help to regulate this balance. So I keep going back to this regulated versus unregulated concept, right? Remember the parts of the tubule that are responsible for regulated reabsorption are, what are the two parts of the tubules responsible for regulated reabsorption? The DCT and the collecting ducts, okay? Keep that in mind. And so structures that are in the DCT and collecting ducts that are responsible for this reabsorption are principal cells. Principal cells reabsorb water and electrolytes, whereas intercalated cells are responsible for acid-base balance. They have to do with secreting or excreting bicarb and hydrogen ions, okay? So the principal cells are involved in the reabsorption of water, whereas the intercalated cells are responsible for the acid-base balance. So make that distinction clear, right? Let's get more into this concept of water balance. So osmolarity is the ability of water to move, right? Now, where does water typically move? From a place of, okay, so it follows sodium, that's one, which brings me to my next concept. It follows sodium, meaning that it does what? So it follows the concentration gradient. And so if we have a place of high water concentration and a place of low water concentration, water is going to move along that gradient from high to low water concentration. What about solute concentration? It's the opposite. Water is going to move from a high or low solute concentration. From low to high. So water moves where there's more solute, right? Less solute, more water. So you have a low solute concentration to a high solute concentration. You have more solute and less water. So think about the movement of water in that way. That's really going to help us understand the medullary osmotic gradient. Okay, this is how water is reabsorbed with the distal tubules and the collecting duct. Now this ties back to that intake versus outtake, which we're not going to stress anymore. Okay. Let's talk about these terms. So normovolemia versus hypervolemia versus hypovolemia. This has to do with blood volume. So how is your blood volume? Is it balanced? Is it too much or is it too low? And this ties back to that water balance scenario. So states of high blood volume would be your positive water balance states, like edema, etc. States of hypovolemia would be your low blood volume. This would be equated to your diarrheal states, dehydration, hemorrhaging, etc. And this is your negative water balance. So just bear this terminology in mind. You probably hear me mention some of these terms as we go along. Again, touching on this concept, we just talked about the movement of water. It follows its concentration gradient, but it moves opposite the solute gradient. So that's something we really want to understand here. This is going to help us understand the measure of osmotic gradient. Water moves where it's high in concentration to lower concentration, or from low solute concentration to high solute concentration. Now, when we get to the medulla of the kidneys, we need to understand that there's a concentration gradient difference, right? Meaning that the medulla is a lot more, what I like to call salty. Salty meaning it has a higher solute concentration. And I'm going to use those terms, and those terms just to help simplify these concepts. All right, where there's high water concentration, I'm going to say watery, and where there's high solute or high salt concentration, I'm going to say salty. Okay? Just bear in mind that I'm speaking about the osmolality and the concentration of either water or solutes. Now, we mentioned before that the cortex is isoosmotic, so it's the same osmolality as the tubular fluid, the fluid in the tubule. And so that's about 300 milliosmoles. Okay? And we have no force for water to move here in the PCT, in the cortex. When we get down to the medulla, this changes significantly. We have a gradient now because the medulla is significantly more salty. It has a lot higher of a concentration gradient, meaning it has more solutes. Okay? And so we have a gradient from the cortex down to the medulla. This gradient is called the medullary osmotic gradient. Okay, the medullary osmotic gradient. And this is the mechanism by which the kidneys are able to reabsorb water and reabsorb salts. Okay, that's sort of the big picture of everything we're going to talk about in the next few minutes. This medullary gradient, this ability for the cortex to be sort of watery, so to speak, and the medulla to be a little bit more salty, so to speak, is how water is facilitated to be reabsorbed in the descending limb, and solutes can be reabsorbed in the ascending limb. We want to remind ourselves here that the movement of water is passive. It doesn't require any energy, doesn't require any transport, it just happens. Okay. This again is hammering this point to death. The proximal convoluted tubule reabsorbs most of the water. This is an unregulated process. The DCT reabsorbs the remaining water, and this is highly regulated by the presence of hormones such as ADH and aquaporins, which we'll talk about later on. So again, just driving these points home. I'm not going to talk about this anymore. We'll talk about this extensively. All right, so let's remind ourselves of the barriers to the absorption here, which are the epithelial cell of the tubule, the basement membrane of that epithelial layer, the peritubular fluid, which sits between the blood vessel and the cellular layer. And so these are our filtration barriers here. This is where we reabsorb. What structure is this image taken from? What part of the tubule? Sounds like a trick question here. What part of the tubule was this, is this cell? How do you know that? That's proximal convoluted tubule. You wrote it in your book, okay. Anyone else? How do we know that this is the PCT? There's glucose moving, thank you. So glucose movement happens only in the proximal convoluted tubule, right? So this image again drives that similar point home, but we do have the introduction of permeating solutes here. And this permeating solute that we're talking about, if you just move freely through those barriers to the absorption is urea. This is the example that we're talking about. We're not going to go into a lot of details about urea, but I do want you to know that it's helpful in facilitating that medullary osmotic gradient. And it's a free moving, because it's so small, it can freely move across the lipid bilayer. It can freely move into the peritubular capillaries. Okay? And this is sort of a repetition of that concept. Right. All right, any questions so far? This is where things are going to get a little bit more steep in terms of the curve. Any questions so far? Alrighty. So we talked about the osmolarity and the difference in osmolarity from the cortex to the depth of the medulla. Okay, we said it was higher osmolarity at the medulla, meaning it's more salty, and there's a lower osmolarity in the cortex, meaning it's a bit more watery relatively. Okay. Now, if we look more closely, what we'll see is that fluid is moving from the proximal convoluted tubule. It's going to move down the descending limb of the loop of Henle. Now, on the side here, the loop of Henle is usually categorized into a thin limb versus a thick limb. For the purpose of this class, we're not going to distinguish thin from thick. We're just going to talk about ascending from descending. All right, and so the descending limb, which is on the left here, is responsible only for the movement of water. That's sort of a big message. So write that somewhere really big or highlight it. The descending limb only allows the movement of water. Nothing else can go. No other solutes, no glucose, nothing else is moving here, only water. It's only permeable to water. And this is a passive process. It doesn't require anything. Okay? Alternatively, on the ascending limb, we do not have the movement of water. This side of the limb is impermeable to water, but we do have the movement of salts, of solutes. So sodium, chloride, potassium are freely moving on the descending limb. Right? Some passive and some active. We'll talk about the exact mechanisms in a bit. But this is the distinction we really want to make here. The descending limb only moves water, and the ascending limb only moves salts. Where are these substances, this water and these salts, where are they being moved to? What is the capillary structure we talked about that is closely associated with the vasa recta? All right, so bear that in mind. We're talking about the loop of Henle. Reabsorption is happening from the loop, either ascending or descending, to the vasa recta, which is the capillary structure. You sort of jump back here. Oops. Okay, so I lost that image, but it's the capillary, oh, here we go. It's the capillary structure that's closely associated, okay, with the loop of Henle. Alrighty? Now, what we want to understand here is this movement is important in establishing the other side. Okay, this is where it sort of gets tricky. The movement of sodium on one side, sodium chloride and potassium on one side, is directly responsible for the movement of water on the other side. And we'll sort of talk more about that, why that's what about as we go on. But I want you to bear that big picture in mind. Water only moves on the descending side, salts only are moving on the ascending side, but they're really tying into each other, they're feeding into each other. Right? This is the counter current multiplier mechanism that we'll talk about as we go on. Okay? So this counter current multiplier mechanism means that if I make the medulla more salty by reabsorbing all of this salt, I now have a concentration gradient on the descending side where water wants to move along its concentration gradient. All right, so think about, again, the osmolarity of the medulla here. We've reabsorbed all this salt, all these solutes on the ascending side. So now this is quite salty. It has a very high osmolarity. And so we have water wanting to go from a high concentration, right, in the tubule out to an area of low water concentration, which is high solute concentration. And so the movement on the descending side directly sets up or facilitates the movement of water on the ascending side. And this is an ingenious system. You can manipulate the movement of these ions and all this water will just start to move. Okay, very ingenious system. You want to bear in mind that the ascending limb is impermeable to water. But the ascending limb of the tubule, we'll talk about the vasa recta in a minute. The ascending limb is only moving salt, sodium, chloride, and potassium. The descending limb is only permeable to water. Alrighty. A lot of students tend to sort of compartmentalize these two concepts, and they're really feeding into each other. And that's sort of where we want to make that connection. That because we have reabsorbed all this salt, we now have a gradient for water to follow on the other side. Alrighty. Hence the word counter current. It's sort of happening in different directions, but they're really feeding into each other. All right, let's talk about some numbers here. Let's talk about the osmolarity. So we start with an osmolarity of about 300 milliosmoles, right? From the cortex to the medulla, this would be around the PCT. We're starting with an isoosmotic situation where 300 milliosmoles is the cortex osmolarity, 300 milliosmoles is the osmolarity of the fluid or the filtrate in the tubule. As we move down the descending limb, what can we see happening here? As we lose water, what about the fluid in the tubule? Is it becoming more or less salty? More or less salty? More salty. So all that water is going into the blood vessel, and so the osmolarity of the tubular fluid increases as we go down the descending limb. We're moving water out of the way until we're left without the solute and it becomes more salty. Okay. On the ascending side, we have the opposite scenario happening. So down at the loop, when we sort of make this hairpin loop here, we have a maximum osmolarity down here. And so as we now change the environment, we change the scenario, we're no longer permeable to water, but only to salts. Salts are being reabsorbed. What do you think the osmolarity is doing at this? Is it increasing or decreasing? The osmolarity of the tubular fluid. It's going to be decreasing, right? It's going to be going right back up to that 300. It's actually going to go a little lower, right back up to that 1 to 200 milliosmoles. All right? And so we have that change in the osmolarity from the descending limb to the ascending limb because we have different movement of solutes versus water, or different movement of substances. All right. So let's look at some numbers here again. The fluid in the distal tubule goes all the way down to 100 milliosmoles. So it goes a little bit lower than that 300 where we started in the PCT. Okay. Whereas if you look at the interstitial fluid, so the fluid that's around the tubule, the osmolarity is increasing from the cortex down to the medulla. Okay, well, let's point that out again back here. Oops. So we have this sort of watery cortex where we have a 300 milliosmoles and a very salty medulla. Okay, so we have a gradient from top to bottom, but then we also have a change in this osmolarity from descending to ascending limb. Now these next series of images help to explain what's going on in all of this. Right? And I'm going to sort of walk us through each of these, and then I'm going to have you just sort of discuss it with each other. This is a concept that may not sink in right away, but with some practice, you'll get better at it. So we have our peritubular fluid, and we have our tubular fluid. All right, now again, we're starting at an isoosmotic situation, so 300 milliosmoles, and as we decrease here, as we go down the loop of Henle, we have up the ascending limb, we have only the movement of solutes. So sodium, chloride, and potassium is being reabsorbed on the ascending limb. What did I tell you that that was for? Why did we reabsorb those solutes on the ascending limb? Why did we reabsorb those solutes on the ascending limb? What is that doing? What is that for? What is that setting up?
Counter.
So that's the mechanism, right? The common current multiplier mechanism, we're facilitating that. But specifically, why are we reabsorbing? So what is the salt doing to the interstitial fluid? One word here. So it's creating a gradient, right? It's creating the gradient that allows water to move on what part of the loop of Henle? The descending. All right, so the movement of salts creates a situation where we have an increased osmolarity. And so now water wants to move along this gradient. We have a salty situation with the interstitial fluid in the medulla. So water's like, hey, we want to go to where there's more salt, right? From low solute to high solute, or high water to low water. Okay, and again, that's passive. Let's continue on. So we have that movement of salts to start, and then water moves to follow, a sort of a reflexive process because of that gradient that was set up.